Hello everyone. Is the mic good in the back or is it too loud? Okay. So, good afternoon everyone. My name is Abdullah Sherif. Today me and my colleague Faisal will be explaining the carbohydrates chapter of the subject biochemistry. Just a disclaimer, this chapter may look very difficult and that it requires a lot of memorization, but once you get the tricks, inshallah it's going to be like a very easy chapter. Okay, so starting off with some questions. Do you have any volunteers? What?
Very good question.
Yeah, okay.
What is the most abundant macromolecule in nature? Carbohydrates.
Yes, correct. Okay. What about this question?
What is the most abundant macromolecule in humans? Protein.
Correct. And in what form do you see these macromolecules?
Amino acid.
Yeah, but then what do you know an example? It's another chapter included in this quiz. Enzymes, exactly. Okay. So you may look at this picture and you're thinking like, what is this stupid picture doing in this presentation? But I want you guys to know is that, or a question is that, what is the primary macromolecule that cells search for when they need energy? Exactly, and what is the process which they utilize this energy? Huh? Exactly. Okay. Next. Oh. Okay. So we need to know that carbohydrates are grouped in two categories before we begin classifying their types. So at first we have monosaccharides, which is basically one sugar only, self-explanatory. Disaccharides, which di means two, so we have two monosaccharides linked together. Oligosaccharides 10 to 15, and then polysaccharides more than 15. I know there was a debate about this point on the group I read, but in the book it's written 10 to 15 directly. So, does anybody know any example of monosaccharides? Oh, okay. Wait, what? I heard lactose in the back.
No, you didn't.
Oh, okay. Okay, and does anybody know any example of any disaccharide?
Sucrose.
Okay, well done. Yeah, so sucrose and maltose, yeah, they are disaccharides. What about polysaccharides?
Starch.
Are you sure? No, I'm not saying you're wrong, I'm just asking, are you
Okay,
sure?
I'm sure.
Yeah, okay. Okay, and there was another polysaccharide which was mentioned in your muscle quiz, if you remember. Exactly, glycogen. Okay. Okay, so carbohydrates are classified according to the functional group they possess, the number of carbons they have, and their configuration. So you may think that I just put 5 to 6, which means all carbohydrates are 5 to 6. No, this is just, I'm using the most common number of carbons in a carbohydrate. And I want you guys to know that there's a really important topic, and I think it was mentioned in chapter 1 but not fully explained, the chirality, which basically means that a carbon contains or is bonded to 4 different groups. Meaning that if I have a carbon and it's bonded to oxygen 2 times, would this be considered a chiral carbon?
No.
Okay. And if it's bonded to 2 different hydrogens, would it still be considered a chiral carbon?
No.
Okay. So I want you guys to tell me what carbon here carbons are the chiral carbons. So like tell me C1 is chiral, C2 is non-chiral. C2 and C3. Okay. And why is C4 not chiral? Exactly. Okay. And I think the rest are self-explanatory, but if you want, you can do them yourself. Next. Okay. So, what is the functional group which is present in all aldoses? Oh, it's written. Okay. Wait. Move it. Okay. So, and sugars that contain a ketone group, what are they called?
Ketosis.
Okay. So, by now you should have memorized the aldehyde and ketone functional group structure. And I want to see if you guys know what is the base sugar which forms all aldose sugars.
Glyceraldehyde.
Yes, glyceraldehyde, correct. And what about all ketose sugars? Yes, exactly. Okay. And then these are structures you should memorize because I saw that they were ticked in your doctor's PowerPoint, so you should memorize these structures by heart. And I want you to bring it to an important point, is that which of these is symmetric and which is asymmetric?
The ketose is symmetric.
Okay.
The first one is not symmetric.
Okay, so thankfully you didn't fall for the color trick, which I put to purposely trick you guys. So glyceraldehyde has 4 different groups. By the way, guys, when we talk about chirality, this isn't considered that we're talking that this carbon is bonded to this carbon. No, this carbon is bonded to this structure here. So this is considered, let's say, R1, and this is considered R2. So in total, this carbon is bonded to 4 different groups. So is this a chiral carbon or no? Okay. What about this one? Exactly. This is why this is an asymmetric molecule, meaning that if this OH were to change here, you are able to basically see that the OH is flipped, which is why it's asymmetric. While this one, if the oxygen is here, could you really determine if the molecule is different?
No.
Exactly, which is why it's symmetric. Okay, so. Well, guys, for this chapter, you need to do a lot of drawing to memorize the structures. Okay, so we have some prefixes that you need to memorize also by heart. So, sugars that contain 3 carbons are trioses, while 4 tetroses, 5 pentoses, so on. And I want you guys to, I have a question for you guys. What is the most common number of carbons found in sugars, basically?
5 to 6.
Okay, amazing. And why is this option incorrect directly?
Because there are no two carbon sugars.
Exactly. So this is a rule you also have to know by heart, is that carbohydrates, anything below 3 carbons is automatically not a sugar. And I took this from your book directly, so. Okay. Heavy topic, but easy. Let's start. So, we have some molecules known as isomers, which are basically same molecular formula but different structure. So, for example, what's the difference between glucose and fructose?
Ketose and aldehyde.
Yeah, okay, but like, give me specific.
The functional group.
Yeah, I know the functional group. Yeah, but I basically mean here is that on this carbon there is this, on this carbon or.
Oh, the aldehyde is on carbon 1, ketose on carbon 2.
Okay, yeah, that can work for now. But basically, the isomers is basically, you know, glucose and fructose have the same chemical formula, C6H12O6. But the difference is the areas where the OH and H's are basically present, or the functional group. So, it's divided into 2, constitutional isomers and stereoisomers. Constitutional isomers, such as the base precursors, we're using this example, they have the same chemical formula. But the difference is that the order that the atoms are connected in. So for example here, this carbon is connected to 2 H's and 1 OH. However, here it's connected to 1 O and 1 H. So basically the whole formula is still the same, but the order in which the atoms are connected is different. This is what we call constitutional isomers. Moving on, the stereoisomers is divided a lot. We have enantiomers, which is basically a sugar which is a mirror image of itself. So for example, if I have a D sugar, which is this palm of the hand, and an L sugar, if we put them in the mirror, are they going to look the same?
Yeah.
Exactly, but if we put them on top of each other, this is the point of enantiomers. And then we have diisomers. So these molecules, when you put them in the mirror, they're not going to look alike, and I think that's straightforward as it is. Then we divide the diisomers into 2 categories. We have anomers, which look the same exactly, but on this anomeric carbon, the OH location is different, therefore we have an alpha version and a beta version of this sugar. Then we have molecules known as epimers. By the way, guys, if they bring you a molecule with the description of an epimer, but they don't give you the choice of an epimer, you can choose diisomer. And this was in our previous quiz, and I remember I got this question wrong, so don't do the same mistake I did. Basically, epimers, same sugar, everything is the same, but there's a difference on only 1 carbon. So look at glucose and look at mannose. Where's the difference? Okay, amazing. So it's carbon number 2. Difference is only 1 carbon, epimers. And then, this is a question, let's see if you guys can do it. Well done, amazing. Clap for him. I won't give him a prize or anything. Yeah, moving. This is a hot topic for the exam, so you need to focus here. There is a rule in which you can determine the number of stereoisomers that a sugar can have, which is 2 to the power of n, where n is the number of stereoisomers, or the number of chiral centers. So here, it says that the number of possible stereoisomers in an aldohexose is how much? What do you guys know an aldohexose means?
6
Aldehyde
carbon
with 6 carbon.
and an aldehyde group.
Yeah, okay, well done. And then, I want you guys to know that this is a rule which is passed down through batches, which I got this rule from the previous batch, is that for ketose sugars, the number of chiral centers, automatically you can subtract by 3. While the aldoses, you subtract by 2. What does this mean? We don't get it, that's okay. This is a ribose. Is ribose an aldehyde or a ketone?
Aldehyde.
Yeah, aldehyde. Yes, it's clear here, aldehyde group. And I think you guys have to memorize this structure for ribose. Huh? Okay. Okay, so this first carbon, is it chiral or not?
No.
Okay, and what about this one?
No.
So immediately subtract 2. This is why we give you that for all aldose sugars you can immediately subtract 2. What about ketoses? This is fructose, but I don't know it.
Subtract 3.
Why? Give me the carbons which we need.
Carbon.
The first 2 are
and
unchiral and the last one.
Exactly. So, generalized rule, when you want to determine the stereoisomers, all aldoses subtract 2, ketoses subtract 3. So, if I give you an aldohexose, how many stereoisomers do you think is possible?
4.
16y and 4y.
Oh, we have to power it.
Yes?
8
Why 8?
because 2 to the power of 3.
Why 3?
3 chiral centers and the aldohexose.
You sure?
Oh, sorry.
No, I'm not saying you're wrong, just keep thinking.
16.
Why 16?
3 chiral
2 times 2 to the power of 4 is 16.
Yes. So, they said an aldohexose. So I'm not gonna draw it fully with the function groups and everything. But basically we eliminate this and this. Oh, did I even draw it? So just imagine that you have 4 carbons left. Because 6 carbons, we remove 2 because they're automatically non-chiral centers. How many carbons do you have left? 4. 2 to the power 4. I think this is just math here. And then find the number of possible stereoisomers between aldopentose and ketohexose. And I brought these figures to help you, but in the exam they don't have to give you the figures. They expect you to just know what to do. So what do you guys think? 8? Why 8?
2 to the power of 3.
Yeah, but this is for only aldopentose. What about ketohexose?
Also, the same thing.
So what's the answer?
8 as well.
How to say?
Because ketohexose 2 to the power of 3 as well.
We have aldopentose, 5 carbons.
Minus
Subtract.
2.
Okay, we have 3.
Three.
2 to the power of 3.
Wait, am I doing the math wrong? 8.
Okay, 8. And what about the ketohexose?
Also, it's 6 minus 3.
So,
2 to the power of 3.
so
8.
Plus 8.
Oh, plus 8. Oh, we need to
I
add them
gave you
together.
and. I wrote and here. There's too much writing here. But there's and.
Oh, we need to add them together.
Yep.
Okay.
Which gives you 16 also. Does anybody not get this point? This is really important, by the way. Okay. Is there no easier way to? Okay. So, this is something I want you all to do as soon as you get your exam paper. This is, as you know, a Fisher projection, right? Where the sugar is basically standing. This is a Hayward projection, where the sugar is basically sleeping, you could say. Curved up and sleeping. So, when you guys take the exam paper, I want you to draw a box. Put OH in the middle, And then I need to draw 4 arrows. Left, down, right, up, whatever. But you just have to follow this formation. Then I want you guys to move clockwise. You're gonna be saying, what's happening here? So, I want you guys to see this OH. This is the Fisher projection. If the OH is to the right, what's gonna be the location of it in the Hayward? Is it gonna be up or down?
Down.
Why?
Because
Yeah, because of the rule, like you just said. So, if there's an OH here to the right, it's gonna be down here. And you guys are saying, why are we not determining the first carbon? Because this first carbon actually doesn't have an OH group. When does it have an OH group? When it begins to cyclize. This is another point you'll see later. But the OH group, when it's on the left, in the Fisher, what's gonna be in the Hayward?
Up.
I'm hearing up and down, so what is it? Okay, up. Guys, this, you're not gonna get it the first time unless you practice yourself. So take a sugar, apply this rule, and then see if you do mistakes or not. What about this last sugar here? This has carbon.
Down.
It's down, right? But look here. Why is there no OH?
Because of the CH2O.
It's on the right.
because it's bonded to O.
Because it's bonded to. When a sugar wants to cyclize, it uses the last chiral carbon here and cyclizes with the first. So an OH is formed here, while the remaining of the molecule, which is here, forms the bond here, and the remainder product is H. If you don't get it, don't worry. We're gonna repeat this later on.
I have a question.
Yes.
Is D and L only in the Fisher projection?
D and L is in both Fisher and Hayward. And there's an important point, but if you want to say it here, is that skip this carbon here. Don't look at it because this is for alpha and beta, as you guys know. What's the difference between these two molecules besides the H, OH, H, OH?
Carbon number 4. The OH down.
No, I'm asking for D and L. What's the main difference?
Carbon number 6.
Yeah, what about it?
Up and down.
Exactly. If the CH2OH is outside the ring, that means it's a D or L? D. While if it's inside the ring, L. So, by the way, when D and L change, they change the OH with them, as you can see here. So this OH was here and now it's here. This one. This is why there's a difference. But you can determine it both in Fisher and Hayward. Hayward, we just said how. In Fisher, if the sugar is D, the last chiral carbon will have its OH to the right. While in the L sugar, I think you guys get it, it's going to be to the left. Is it clear?
Yeah.
Okay. Oh. Okay, so this is what I was talking about, is that usually when the sugar is normally standing, before it begins to basically sleep and curl up, which is the cyclization, you can't determine if this sugar is alpha or beta. By the way, guys, the first sugar, or the first carbon actually, when it will begin to cyclize, this will be the determinant if it's alpha or beta. In the case of aldoses, in the ketoses it's a bit different, we'll see that later. But you could see here, when it began creating a bond with the last chiral carbon and the first carbon, you can see here the OH disappeared. What was the result of this? There was an O here, and there was an H here. So the OH was used basically to create a bond and help create a OH on the first carbon. Do you guys get this? Because this is something I was confused about when I was foundation. When the sugar is in alpha form, the OH is to the right. And this is the Fisher projection, right? Okay. If this sugar were to basically curl up, where would the location of this OH be? Up or down?
Down.
Down. Any doubts? Why it's down? Okay. And, huh?
The square
Yeah, exactly. And what about the beta?
Oh.
Yeah.
Self-explanatory. However, this is a rule you have to memorize by heart. And if this was too hard for you to memorize, which is up beta down alpha, I want you guys to think that we said, I didn't mention it, but it was written, that naturally occurring sugars are all in D form, okay? So, when you guys woke up right now out of M27B and look in the sky, what are you gonna see?
Clouds.
Besides clouds, I mean animals. Birds. So, consider the birds are OHs. Where do birds normally fly? Exactly, up. So if the OH is up, it's beta. Are you guys getting it? Okay? What's abnormal? So, do you guys see birds flying on the ground? Which is why you have abnormal for alpha, when the OH is down.
Can you show us an example in the
Okay. لا لا بي. Okay. So let's say, for the sake of explanation, we're gonna ignore the L because it's gonna flip the rules around. We're gonna say it later. But let's say the sugar began to cyclize. Began to cyclize. And there was an OH group here. Where would be its location? Why up and why down? It's down. For those who said up, what's the reason for your answer?
Because birds are up.
I'm saying that this is for naming, not for actually putting the OHs. So when the OH is to the right in the fissure, it's going to be down in the hayward. And what's the name of the sugar? Alpha sugar. So when the OH is down in a D sugar, which is normal, the birds would be flying down on the ground, which is abnormal, which is why it's called alpha. However, if you wanted this to be a beta sugar, remove the OH here, put it here, move this here, and make the OH to this. Since it's left, it's going to be up in here, and this is where birds fly, so it's beta. Wait, is this clear for the person who said? Most of the person who asked. Is it clear?
Yeah, yeah.
Okay. This process you're seeing here, or this reaction, it's not really that important for the exam, but you have to know it regardless, because then you'll say you didn't say this in Pacademia or whatever. So, this aldehyde group, or generally, aldehyde groups and ketones, when they react with alcohol, they form either hemiketal or hemiacetal, respective of their names. So I guess it makes sense, by the way, hemiacetal, hemiketal. This alcohol, important piece of info, but I don't know how you're going to utilize this. This alcohol does not have to be in the same sugar. So this alcohol may be from another molecule directly, and it reacts and it creates a hemiketal or hemiacetal. Doesn't have to be from the same sugar. I don't know what to do, what you guys are going to do with this info, but most likely you won't be questioned about the location of the alcohol. When these sugars begin to cyclize, and do you guys remember when I mentioned in aldoses, when they want to cyclize, what carbon are they going to attack?
The first one.
Exactly, the first one. This is in the case of aldoses. But look in ketoses. Which carbon do they attack?
The second one.
Exactly. They attack the second. Which is why the bond was formed in this irregular way you see. And usually, this is something I used to do and then I realized I was doing it wrong, is that whenever I see the sugar, I immediately thought, oh, I was looking at fructose immediately. This is not the case. Even though that this may be here, but in some questions they love to switch this and confuse the students. But this form is called a furan form, which is basically a 5-member drink. Sugars, mostly 5 to 6 carbons, when they want to cyclize, they either assume the 5-membrane ring form, which is furanose, or 6-membrane ring, which is pyranose. These sugars can switch between these forms as much as they want. And the useless piece of information is that fructose has to be in furanose form. It's written in the book. I don't see how this is going to affect your life.
I have a question.
Yes.
In this case, the ketone bond is in the second carbon. If it was in another, like the third or fourth carbon, does it still form a cycle with the second carbon?
No, I don't think that, like, biologic it shouldn't, because honestly, I don't know about this point. I'm gonna get back to you after Pacademia research, okay? Don't forget this question. Keep remembering. Oh.
Is ketone always in the second carbon? Is the aldehyde group always in the second carbon ketone? For it to form a cyclic?
Usually, yeah. When the examples we're gonna see later on in the reactions part with Faisal, you're gonna see mostly that fructose loves to basically use the second carbon, not the first.
Only fructose or all ketones?
No, ketosis in general, because actually you need to know that in some cases ketones don't love to react as much as aldoses. So you'll see. Okay, so this is a process. Well, this chapter is filled with so much information that you can get overwhelmed, but you need to focus on the important things. This medium, you don't need to pay attention too much to it, but basically they're telling you is that when glucose is submerged in an aqueous solution, so basically distilled water, pure water, it by itself, by its nature, it determines, do I want to be in the beta form, alpha form, pyranose form, or furanose form? So you can see here that, for example, fructose loves to be in the furanose form, but glucose can switch as it wants. It can be in the furanose form, and it can switch between beta and alpha. Something you need to know, this is important, is that the majority of the glucose form, when it's in the aqueous solution, is beta-D-glucopyranose. I remember there was a question, I'm not sure, I'm gonna check back, but this is important. You need to know what form does glucose take mainly. And sugars that are capable of doing this leave an open chain. This open chain can basically participate in oxidation reduction reactions. So if a sugar isn't able to do this, they can't do reactions. Oh.
Okay, so hello, I'll be سامعين انتو? Do you hear me?
Yes.
Okay. So I'll be talking about the reactions of carbohydrates. So we have 6 reactions. Can anyone list them all? Yeah, you saw some of them, but can you list them all? Anyone?
Oxidation.
Okay.
Isomerization.
Okay. No, there's no substitution here.
Transference.
Glycoside.
Yeah, glycoside, yeah. Yeah. There's no methylation.
Glycation.
Okay, so we have oxidation, reduction, isomerization, esterification. No one said esterification. Glycoside formation. You said?
I said it twice.
I didn't hear. And glycation. And we have another one, a 7th one, glycation. But it's not here, but I will explain it later on. So the first reaction, oxidation. So in the presence of an oxidizing agent, we'll have the monosaccharides because they rapidly oxidize. So they undergo several oxidation reactions. So we have 3 types, 3 different outcomes. If the aldehyde group is the one getting oxidized, we have aldonic acid. In this, it's a glucose, so it's called a gluconic acid. Is that clear? And then we have the oxidation of the terminal. Yeah, we have the oxidation of the terminal methyl group. So when it oxidizes, it's called a uronic acid. Yeah. So this is a glucose, so it's a glucouronic acid. If both of them are oxidized, it's like this is not showing here, but if you it's not showing anywhere. But if both of them are oxidized, it will be an aldaric acid. So this is a glucaric acid. So here I put a quick summary, like just an aldehyde oxidized, aldonic, terminal methyl, uronic, and both ends aldaric. That's pretty much it. So lactose. So the carbonyl groups of both aldonic and ionic, not aldaric. Aldonic and ionic. These can react with the OH group of the same molecule, the same monosaccharide. So they'll form a cyclic ester, which is like this. This is a cyclic ester. It's called a lactone. So, and an example of it is an absorbic acid, which is a vitamin C derivative. So, here we have the carbonyl group here, and the gluconic acid. It goes and cyclizes to form this. You have to know the general structure. Like you have to know that this, if this is here, it's a lactone. You have to know this. I know it's not ticked, but last year they got something like this. And I put something to put it simpler to you. Imagine this. This is thing. It represents this one. Or this one. It doesn't really matter. Okay? So this one, the snake. Imagine this is the carbonyl group. And this is an OH. So imagine the terminal group goes and attacks the OH group and forms a cycle. And that's just basically the idea of the reactor. Is that clear? Anyone has any question about it?
Is that the case only in lactones?
What do you mean lactones on?
In the tricyclic
No, there's the Fisher and Helmholtz, that's one. But the difference between the Helmholtz structure is this one, the double bond O. That's what differs it from, that's what makes it a lactone. Is that clear?
yeah.
I have a question.
Yeah,
Why-
sure.
Why can't a direct form cyclic mix cyclic?
Because it's oxidized.
Okay. You see, it's not. Okay. Big Fag, can you move with you?
It's okay, I
Okay.
have the picture.
Okay, because you see, there's two carbonyl groups, so like it will cause repulsion. It won't close because like these are charged and things. But you don't have to go into these details, yani. Okay. So like, is there anything that's not clear? Anything, general, from where we can? Okay, we'll go move on. So the things, the reducing sugars that are oxidized by a weak oxidizing agent, these are called reducing sugars. So a general statement is that all aldoses are reducing sugars. That's a general statement. Like if you get an aldose, it's a reducing sugar. And why are they? Why is it like that? It's because that they reopen when they're in the chain, the Helmholtz structure. They reopen and form an aldehyde group. This will act as a reducing sugar. So there's exception to this. Like not only aldoses, some ketoses, like fructose, are reducing sugars. Why is that? Because it's converted to an aldose with isomerization. As we explained what is isomerization before, and I'll explain it again later on. So I put this image for you to imagine. Imagine the inside the box is a reducing sugar. So you come and claim the reducing sugar. So imagine the key. The key is an aldehyde group. So it opens it and claims the reducing sugar title. But fructose is a ketose. So imagine it as a rubber coming with a key lock and like rubbing it. So that's like a simple idea to just remember, yani. If that was not clear, did you get it, reducing sugar idea? So like if I ask a question, you would know, right? Okay, we'll go over the reduction. So if an aldehyde or ketone group get reduced, they form a sugar alcohol called alditol. And like glucose is an example. So you have to know this name just in case they get you like which of the following is a sugar alcohol. So you know that is D-glucotol or D-sorbitol. Like I think that's just pretty much it. So like, and you can see the difference in structure, but you don't have to know the structure. I think, is that right? You don't have to know the structure of the D-glucotol. Okay. Okay, so we went over this, but I'll go over it again to explain my other idea. So isomers are like the same chemical formula, but different structure. So we have 4 examples of them: fructose, glucose, mannose, and galactose. They are all isomers. They have the same chemical formula, which is C6H12O6. And these are the structures. You have to know them by heart because they'll ask you about it. So I'll just give you a refresh your memory because I'll go over the next part. Okay, indiols. In a basic solution of alkaline, if you place glucose in it, it will, over some time, it will cause some changes, isomerizes it to mannose and fructose. So this, why does this happen? Why do you think this happens? It's just like, why does this happen? Why does it change?
Can you repeat the question?
In an alkaline, why does it change in an alkaline solution?
Does what change in deal?
In glucose to mannose and fructose. Why does it change? Why does it change from glucose to mannose and fructose?
Because the hydrogen atom moves.
Yeah, okay. The hydrogen atom moves and the double bond shifts. In this process, when this happens, you will have an indiol intermediate. This is just like a way to simplify the reaction, because like instead of jumping, it goes like through this reaction. And that's all you have to know. And I put this picture like to show you that this is the glucose. It's basically the same thing, the same structure, but different things. So like different hydrogen, different double bonds. That's like the basic idea of it. So when you have a hydroxyl group, which sugars have many of, they react with acids and form esters. And they can form two different esters, phosphate esters and sulfate esters. And I heard that phosphate esters are not included for you. Is that right?
Yes.
Okay. So I'll just go over the sulfate esters. And imagine esters as a decoration that comes and makes the sugars less reactive. That's like the idea of it. Okay, so sulfate esters. Where are they found? In proteoglycans. What are proteoglycans? I explained in the last part of the chapter, so it makes more sense. But just know it as proteoglycans. Not you know what's the idea of it. So these sulfates, what do they have? They have negative charges. They have many of them. So what do? They pull water and ions. Which ions? Positive ions. And this pulling of water and ions make the cell more flexible and more hydrated. So this helps for salt bridging between sugars. That's the basic idea. Is that clear for everyone? So, we discussed how hemiacetals are formed. Does anyone remember how hemiacetals are formed? We just discussed it with him.
Aldehyde with alcohol.
And hemiketals?
Ketone gas.
Okay. So to form an acetal or a ketal. Okay. So to form any one of them, we have to get the hemiacetal and react it with another alcohol to get a ketal or an acetal, which is glycoside, which is a type of glycoside. So when you do this, you form a glycoside linkage. And this is called a glycoside, which is, as I said, hemiacetal to acetal or hemiketal to a ketal. And it forms H2O, but I don't think you have to know this, but no, it's better. And if it's from glucose, it will be glucoside. If it's from fructose, it will be fructoside. And if it's 5-membered phonoside, which we discussed the idea, 6 members pyranoside. Is that clear?
Is that only for cyclic ones?
This one is like, you can say it's for, it's general, but like it's mostly for cyclic ones, yeah?
This naming is for membrane rings. So
Mm.
you can't form a membrane ring without cyclizing.
Mhm.
So you have to have cyclizing.
So, we discussed the glycosides, we now discuss the properties of them. So they are stable in basic solutions, and they do not react with Venn-Tix reaction. What does this mean? It means that it's not reducing. Why is it not reducing? Because the ring is locked, so it can't mutate. So it's locked in this position, and it can't show an aldehyde group. So, but what can show an aldehyde group is hemiacetal. Because why hemiacetal? Because acetals. So like acetal will have an aldehyde group. So it can act as a reducing sugar. And when two monosaccharides join via glycosylated bond, it will form a disaccharide. And if there's more than one, more than two, especially more than 15, that's what's mentioned in your book, it's called a polysaccharide. So I put this photo. Why do you think I put this photo? Okay, I put this to show you an idea. Imagine you have a glycoside, like an acetal. Let's say an acetal or a ketal. You try to open the door, it's locked. So you can't reduce the door like as this. It's not a reducing sugar, so you can't open it. And if you inhibit acetal, it can really open easily because it's an acetal and it has an aldehyde group and opens really easily. Is that clear or did I confuse you?
Can you explain it again?
Okay. Imagine glycosides. Glycosides, non-reducing, can't react with Venn-Tix solution. So because why? Because they're locked. So why did I put this? Imagine this door is locked, so you can't open it because you can't open the ring. It's locked like that. That's it. Is that clear?
Yeah.
Glycosylation reactions. So, what is this? It's a reaction where we attach the glycan to a protein or a lipid. which by forming glycosidic bonds by glycosyl transferase. You have to know this enzyme. I think it's better to know this enzyme. And where does this bond form? Between the anomeric monosaccharide carbon, or any carbon, the reducing sugar, not reducing, sorry, of just a sugar, and nitrogen or oxygen. And what does this, they have two names. What are they named? It's terrible. Okay, N linked and O linked. So I put this photo. Imagine this is just a protein. It's just a protein. There's nothing linked. But when you do the glycosylation reaction, you design it and make it look nice with glucose or sugars generally. So like that's just it. Glycations. So reducing sugars. This is the one. That's why I said reducing sugars last time. This was the one. Reducing sugars react with nucleophilic nitrogen. So the idea of them is that they occur. They don't need an enzyme to happen, but if you heat them, they occur really rapidly. And this is like an example of it. I don't think you need it, but know that lysine residue is an example of a glycation reaction. So now we have questions. If you answer, I'm not going to give you the candy. Okay? So this is the question. Who wants to answer? Okay. You. صح. Okay, this one. Yes, see. And if, what makes it a correct statement? Can you correct it or can you not? C. يلا.
They can be aldonic or uronic.
صح. Okay, this one. يلا.
Because it isomerizes in the nitrous form.
D.
هو صح C.
C.
Okay, you. What? Yeah, A. Okay, this one. Who wants to answer this? Okay, you in the middle.
The rings are not.
Yeah, right. This one.
C.
Yeah, correct. Okay, Michael, you can.
Okay, so for the last part of the chapter, I'm going to be explaining its monosaccharides and all the things which follow after. So, what do you guys know the most famous monosaccharide? Okay, so this is another name for glucose, and honestly, I've had trouble memorizing this name. So my thinking was that you guys know the show Dexter, the guy who kills. So he kills. There's blood. What's the main sugar found in blood? Glucose. So relate them how you want, but this is the method I used. So it's the most abundant sugar in your blood, and it's useful for cells that don't have mitochondria. And if RBCs don't have mitochondria, what do you think they're gonna do? Like, I don't think this is mentioned, but I just want to test your high school knowledge. I heard two answers. Who answered? I heard the answer. Yeah, but how?
Anaerobic glycolysis.
Exactly. Okay. So, and also for organs that don't have oxygen or they have a limited supply. So, glucose, if you don't eat a diet with glucose, it's completely fine because we can easily get them from lactose, maltose, and sucrose, but not cellulose. Why do you think?
Cannot digest them.
Yeah, why?
We don't have the enzyme that digests.
Exactly. So, I want you guys to basically tell me why the location of the OH is here and why it's here, based on this figure, the top one, which is for basically glucose. I want you guys to tell me OH is right, so it's down.
Number
OH
D is on the right.
Which one?
Number 3 is on the left, so it's up.
Okay, that's correct. And then?
And now
Number four is on the
number
right.
both of them.
Yeah, okay. Well done, actually, you guys are getting it. Okay. What about this question?
Convenient.
Okay. And another question, which I didn't write, but I'm just saying it here. What reaction forms a glycosidic bond?
Dehydration.
Dehydration. Why is it dehydration?
Condensation, forming of water.
Huh?
Condensation, forming of water.
Exactly. And what properties does a glycosidic bond follow? I think it was an amide or an ester. I'm not sure. I'm gonna get back because that's a really important one. Okay. Fructose. This is the sugar which you find in fruit. So who here is a fruit enjoyer, fruit lover? No one? Okay, so you love fruits. What's the main sugar found in fruits? Fructose. So you love this sugar, so it's levulose. It's twice as sweet as sucrose. So businesses, instead of putting too much sucrose, they just say, why not just put a less amount and just put fructose instead? Even though fructose, high quantities of fructose is associated with age-related diseases. What does this mean?
Alzheimer's and that type of stuff.
It is, but actually the word is misleading because it says something, but it's completely something else.
Isn't it a carcinogen?
Not that I know of, no.
Does it mean coronary diseases?
Exactly. Fructose, because it can undergo glycation 7 more times than glucose, which means it can form byproducts, which can stick in your blood vessels and possibly cause. Did you guys hear of arteriosclerosis?
Yes.
Yes. If you eat too much sweets, like your parents tell you don't eat too much sweets, it will be bad for you. This is one of the main reasons, but they don't even know, they're just saying it. Fructose, use this piece of info, but don't expect that this is going to come in the exam, but just know for your own sake. Sperm cells in the male reproductive tract love to use fructose as the primary energy source. And I want you guys to tell me, ignore this. Can you like name the structure from here? And the OH is to the right, same thing? Or do you guys get the idea already? Are you guys confident that you're able to convert a Fisher to a Hayward?
Yeah.
Are you sure? لا حط السؤال ده. امشي امشي. Galactose. The most annoying sugar out of all monosaccharides in my opinion. It's really important in milk. Why? And not besides milk actually, because that's for lactose. They both share kind of the same function. But galactose is very important for glycoproteins. Oh, I read glycoproteins 2 times. It should be glycolipids here. Lipids. And phospholipids and lactose. I highlighted the main ones that I think you probably, if you're going to be asked, you're going to be asked to mention one of these. If you don't eat galactose, don't worry, your body got you. Because you can generate galactose from a molecule called glucose 1-phosphate. And don't worry, this may look like a weird molecule. When you reach biochem 2, you will know this molecule by heart, don't worry. And then, if you don't have the enzyme necessary to break down galactose completely, what do you have?
Galactose.
Yeah, and besides biochemistry, what do you guys think is possible to do for a person who has galactosemia? Just, I want to see your brainstorming skills.
Accumulation of galactose.
No, I'm saying, what should you do if a person has galactosemia? Like, how should you help him? Because you guys are going to be doctors, you need to think how to help patients. Well,
Don't feed them galactose.
yeah, exactly. Just give them a galactose-free diet and a lactose-free diet, because lactose will be broken down into galactose later on. When galactose begins to accumulate, here we have a big problem. This can cause liver damage, mental retardation, and cataracts. Does anybody know what cataracts is?
Yeah, the blurry eyes.
I got 2 answers.
Isn't it with the eyes?
Okay. Whatever you say, I myself don't even know cataracts. Okay, guys, leave this sugar. Basically, I want you guys, I gave you this name, alpha D galactose. tell me the location of the OH on H. Basically, I want you guys to tell me if it's going to be an H or an OH, based if it's alpha D galactose. So the first,
Oh. Because the down, because it's up.
so is it H or OH? I only want. Okay. Okay. And what about the second one? Do you guys memorize the structures? Okay. Well, we have to we have to memorize them. Okay. So starting, glucose. I can't give the middle finger here because we're recording, yani. But I think, yani, this is enough, yani. So you see here, I want you guys to begin counting from the thumb here. This, for example, the thumb is carbon number 1. So this is carbon number 1, and then you have the. Okay, so anyways, this finger, which is finger number 2 or carbon number 2, is not extended. A rule here, if you want to memorize, the extended finger is going to be where the OH is.
The thumb is the first chiral carbon or the first carbon?
The first carbon in this case, because the sugar didn't cyclize, so it's not chiral. Yeah, don't confuse yourself, yani. When they gave you this structure, the only chiral carbons you have here, 1, 2, 3, 4.
What does closed and open mean?
No, there's no difference. Yeah, I got asked that same question. There's no difference. This is just variation, so they don't confuse you. Okay, so middle finger. Which carbon has the OH outside? Which carbon? Okay, 3. Which is why on glucose, the OH on carbon number 3 is to the left. It's the only OH to the left. Well, what about mannose? For this is really easy, because when you imagine a man holding a gun, he's gonna do like this. So, OH, OH. Carbon number 2 and carbon number 3. I think this is easy, right? Okay. And then you have galactose. Galactose is just like glucose. It tries to be the same, but it just has an extra OH, or not an extra OH. It flips its OH on carbon number 4. So, continuing from that structure, what do you guys think is going to be here? H or OH? And what carbon is this?
3.
How is it 3?
1, 2, 3.
1, 2, 3, 4, 5, 6. You guys have to name it like this, you have to number it like this. So, on carbon number 2, where is the OH? To the left or to the right? Guys, come on. Carbon number 2, where is the OH?
Right.
Wait. Oh, I'm looking at glucose. Okay, my bad. So the OH is to the right or to the left?
Right.
Okay. If it's right in Haworth, what is going to be? If it's right in Fisher, what's going to be in Haworth?
Down.
No. So there's going to be an OH here. What about carbon number 3 for galactose? The OH is to the
Left.
Wait. Oh, it's in, okay. I thought I was reversing the direction from. Okay, the left. So what's going to be?
Up.
Up.
Again up and then low.
Okay, by the way, guys, this is really important. To be able to basically convert Fisher to Haworth, this is going to help you so much in this quiz. You don't even know. Okay. Now we have some derivatives. Of course, your cell doesn't just want monosaccharides. They have to play around with the monosaccharides. So, the beginning, we have, as Faisal said, that when this terminal CH2OH is oxidized, you get uronic acid. So we have 2 examples. We have D-glucuronic and L-idiuronic. So, D-glucuronic is in its alpha form. I don't think they're going to ask you about this, but this chapter just has a lot of useless information. So, D-glucuronic. I want you guys to tell me, which of these is D-glucuronic? I forgot to mention that's alpha here, so this should help you a lot. This should just give you an answer directly.
First one,
Why?
because the 6th carbon is up. Last
Okay, yeah, that's true, but okay. You gave me the correct answer, but I wanted you to focus that it's alpha or beta. Since it's a D sugar, the alpha or the anomeric carbon is going to have its OH group down, which is why it's called alpha. While the L-idiuronic is L sugar, so the CH2OH, which is the terminal group, which was oxidized in this case, which is why it's missing some atoms here, is pointed down. So it's a D or L sugar. You guys, you need to be more confident when you answer. So, L-idiuronic is an emitter of D-glucuronic. This is just something you have to know. D-glucuronic acid, it's important for producing steroids and removing toxic molecules from the liver. And you know the breakdown of RBCs, what does it give you? Or do you guys not study that? Okay, in Bio 2 you'll study that when RBCs are broken down, the heme group is converted into another molecule and then it ends up as bilirubin in the blood. This D-glucuronic is important to mix it with bilirubin to make it more soluble in water, easier for the body to get rid of. So I think you're able to identify which is D-alpha glucuronic and which is L-beta-idiuronic.
I have a question. Why, if it's beta, why is the OH down?
Which one? This one?
Yeah.
Because when D sugar, we basically said that if the OH group is above, what's gonna be?
Beta.
Okay. And if its OH group is down?
Alpha.
Okay, this is in a D sugar. This is a L sugar. You flip the rules.
Oh, okay.
So, amino sugars is basically, you take a sugar, you attach an amino group, and then you can attach whatever you want. So, sugars, they love to bully carbon number 2. Anything they want to attach, they're gonna attack carbon number 2. So, this conjugation of a carbohydrate with a protein or lipid, it can be both. Doesn't mean that it's only one. This is important, by the way. Which is how we form glycoproteins and glycolipids. Okay. This has two derivatives, which are just pure amino acid with a glucose structure, or with a sugar structure. We have D-glucosamine and D-galactosamine. Which is D-glucosamine, which is D-galactosamine? By the way, you don't have to memorize, but if you got through the explanation, you should be able to identify which is galactose and which is glucose.
First one is glucose.
Why?
Because there's only one that's in the that's going up. Which is the
Third one is upward, so it's glucose. For the first structure.
Third one's upwards, okay. But galactose and glucose both share the OH and carbon
Yes,
number
but-
3.
Carbon number 4.
Carbon number 4. You were saying the same thing? Okay. Good. So this is glucosamine, this is galactosamine. Why is it called amine? And then you have some amino sugars. Besides, we took the sugar and we gave it an amino group. That's not enough. We have to add an acetyl group. Some examples is N-acetyl glucosamine and N-acetyl uramic amine. So, by definition, what do you think this basically is? Think about it. Yes, on what molecule? On what sugar? Simply no. These names look complicated, but when you divide them, it's really easy. And then this one, I'm not expecting you to know it. And then this N-acetyl acid is a common form of salicylic acid. It's formed basically D-manosamine pyruvic acid conjugate together. Is this important? Just know it for your own sake. So you don't get an exam and you're surprised. Then you know salicylic acids are ketoses that have 9 carbon atoms, amided with acetic or glycol. This information, honestly, I don't think you're going to be asked, but just know it so you're 100%. Okay. Okay, but guys, are you getting the information or is there anything which is not clear to you? If there's anything not clear, it's okay. Say. Okay. So, monosaccharide derivatives. Another part of them is something called deoxy sugars, where we take a sugar. So basically, let me draw this for you here. Take a sugar. Imagine there's an oxygen here. On a specific carbon, doesn't matter here, but in a specific carbon, instead of having an H, we removed it and we put an OH. This changes the whole sugar's name into a deoxy sugar. Base rule. This is something you have to know. Important examples of deoxy sugar is L-fucose and 2-deoxy-D-ribose. Where do you guys find this? DNA. And if we remove the deoxy group or we remove the OH, where are you going to find this sugar? Think about it.
RNA.
RNA. Exactly. So, fucose, guys, you know that your blood is AB positive, AMI, these whole groups. Part of the thing which helps determine your blood type is L-fucose. You see, there's so much useless info. Now we're getting to the really important parts. Disaccharides. The first disaccharide we have is maltose. What is maltose? You guys, besides reading, what is maltose?
Table sugar.
Okay, yeah, but I'm asking, what is maltose? What's the composition of maltose? 2 glucose. Why is it alpha 1,4? Ignore this. This is cell bios. Why is this alpha 1,4?
Because the bond is at alpha 1,4, at 1,4, carbon 1 on the left structure and 4 on the right structure.
That's part of why it's 1,4, not why it's alpha 1,4.
Alpha because the OH on the last one is down.
Anomeric carbon.
Is it? Because if that,
Anomeric carbon is up, right?
wait.
The anomeric
Wait,
carbon
wait.
is in the alpha configuration. The OH is down, is the opposite direction of the terminal EC.
I didn't hear any of that one. Can you
I
repeat?
mean, it's alpha 1,4 because the anomeric carbon in the one on the left, the sugar on the left, its OH is in the opposite direction of the terminal with the carbon 6.
You have partially the correct idea, but you mixed it up in the end. Guys, if the bond is down here, what do you think the OH group before the bond was created was the direction of it?
Down.
Down, which is what alpha beta?
Alpha.
Alpha. And the bond remained down. So what is the bond? Is it hard? Yani? I think it's pretty straightforward. Yani. And for any confusion point, why is this beta maltose? Why is this alpha maltose?
Because of the
first
anomeric
carbon.
and the
Exactly. So when we want to name the bond, we don't look at the free anomeric carbon which is just sitting there. We look at the carbon which was used to create the bond, which is here. So carbon number 1 bonded with carbon number 4. The OH group was down, so the bond is alpha. And then we want to name the sugar, not the bond. The sugar, we look at the free anomeric carbon. Is this difficult? No, honestly, I'm asking because if you want, I can repeat.
Yeah, could you repeat?
Okay. This sugar, this is 1 glucose, this is 1 glucose. We agree? Okay. What carbon did the first glucose use to bind to the second glucose?
first carbon. The first carbon and the fourth carbon.
Exactly. And usually, guys, Faisal, I want to go to the structure of glucose. Okay. Guys, what determines if a sugar is alpha or beta?
The direction of the aromatic carbon.
The last carbons used to determine if a sugar is D or L,
The
not
anomeric
alpha.
carbon.
The anomeric carbon, which is in this case,
The one after the oxygen group.
yeah, what number is it? Carbon.
Carbon is it not 1?
It's 1, yeah. Guys, are you confused on this part? Are you sure? Okay. Let's go back to the maltose. Because we need to, guys, you need to build on concepts. You don't learn something and then move to something else. So here, this maltose used, or let's divide them into the actual monosaccharides which were used. This glucose used carbon number 1. It used the OH group on the anomeric carbon it had, and then bonded to carbon number 4. So Guys, and think about it. The anomeric carbon is the big boss. If we want to determine the bond, do we look at the carbon which is just normal, or we look at the carbon, the anomeric? Louder. Anomeric. Okay. So we want to name the bond. The anomeric carbon here, the poor anomeric carbon, had its OH group here when it was bonding, مسكين. And then it lost it by creating this bond. So do you think يعني مين اللي عنده حق يسمي البond؟ Carbon number 1 or carbon number 4?
4.
Why 4?
Because it's anomeric.
Are you sure 4 is anomeric or 1? No guys, I don't want you to, just because you got this wrong now you pick this. No, I want to know the reasoning.
It's the anomeric carbon, so it's the first one.
Carbon number 4, in this case, unfortunately, it's not the anomeric carbon. The anomeric carbon is the first carbon. So guys, when we say anomeric carbon, when you want to determine if a sugar is alpha or beta, or the bond is alpha or beta, you look at the anomeric carbon. So when you want to determine if this sugar, يعني, ignore this here. If you want to name this sugar alpha or beta, do you look at this carbon or this? The first one, exactly. So how is this one the anomeric carbon? Is it clear now?
It's easier that the anomeric carbon is directly after the oxygen. That's an easier way to remember.
Yeah, true. You can use that. Yeah, what he said. So what he was saying is that usually the anomeric carbon is after the oxygen, which in most cases is actually true. I didn't notice that. So is the anomeric carbon here, or is the carbon here after an O? Let's use his idea. Is the carbon here after an O? Okay. Then is it an anomeric carbon? No. So it doesn't have the right to decide if this bond is alpha or beta. Are you getting the idea? Is that the anomeric carbon, it decides if the bond is alpha or beta. Is this clear?
No.
So okay, so the anomeric carbon on the first glucose unit had its OH down when it reacted with carbon number 4 on the second glucose. So by logic, who has the right to name the bond? The first carbon or the fourth? The first, because it's the anomeric carbon. And if its OH group was down, what's gonna be the bond? Alpha or beta? Alpha. Alpha what? It's simple, but you guys have to repeat and understand these concepts individually. And why is it called beta maltose? You guys said the same thing, but you cut out each piece. So you look at the free anomeric, you look at the free OH on the anomeric carbon. If it's up, it's beta. If it's down, it's alpha. The sister or the sibling of maltose is cellulose. Same thing exactly, completely, except that it's just flipped the bond from alpha 1,4 to beta 1,4. Is there something such a huge variation with them? Not really.
I have a question. Here you told us that before the bond happened, the OH is down. That's why it's beta.
No, that's why it's alpha.
Because it's anomeric.
What?
What's the difference between the first one and the second one? There's no difference.
There is a difference. Look at the location of the OH group here and here.
But aren't we looking at the anomeric carbon?
This is the anomeric carbon, and the other anomeric carbon on this glucose was used to create the bond. So we lost it. مع السلامة خلاص. يعني there was 2 anomeric carbons. يعني wait. I need a white screen. We'll ignore whatever this is. Okay, so let's say this is a glucose unit. Where is the anomeric carbon here?
The first one.
The first one. And then we have a second glucose unit. Where is the anomeric carbon here? The first one. So both have their own anomeric carbon. يعني كل واحد لحاله. But when they wanted to bind or to create a bond, this glucose had to sacrifice its, oh, no, it should be down. This glucose sacrificed its anomeric carbon to create a bond. And since this glucose had its OH down, when it created the bond, when the OH is down, what do you call it, alpha or beta? Alpha. So if the OH is down and it created the bond, is it going to be an alpha bond or a beta bond? You.
Okay, yeah, but my question is, we don't know where the OH was before, like, the bond happened.
Okay, but if that's the case, then how is the bond drawn down?
So if the bond's drawn up, the OH was up?
It's up. And if generally, if you want to link the events together, yes. But usually people just use a lazy rule, is that if the bond is up, it's beta, if it's down, it's alpha. But
In the other picture, both of them were down, and one of them
exactly,
was up.
yeah. And the bond was still alpha 1,4 in both molecules. But what was the difference was that in the alpha, the beta, the OH was up, which is why we called it beta maltose. But in the other picture, the OH was down. So we called it alpha maltose. So when we're naming the sugar, we don't care about the bond anymore. We know the bond is there. We're not going to change the naming of the bond. But to name the sugar, we look at the free anomeric carbon. If it's up, it's beta. If it's down, it's alpha.
So naming the bond is different than naming the sugar.
Naming the sugar depends on the free anomeric carbon. But naming the bond itself, you look at the bond direction. And this actually can get very messy because, for example, let me tell you, before we move on to cell bios, if this sugar has its CH2OH inside, what direction is this bond? Is it alpha or beta now? Guys, in an L sugar, if the OH is down, is it alpha or beta? Beta. Alpha if that was a D sugar, which is normal. Yani we're taking something, we're making it not normal, and we're flipping all the rules. Okay?
How do I know if it's a D sugar or an L sugar?
If the CH2OH is inside the ring, it's an L sugar. If it's outside the ring, it's a?
If it's outside, then the OH down means it's alpha.
Yes?
And if it's the CH2 is inside, then OH down means beta.
Yes. And I put some rules in the presentation. Later on, when you review them, just memorize these rules by heart. I kept them in the slide. Is this clear? Okay, we're back. So, why is this bond called beta 1,4 in cell bios? By the way, if you're confused which structure is cell bios, it's this one. Why? Anomeric is up. So what direction is the bond? Up. Guys, when you memorize these small tricks, I swear to God, this chapter becomes one of the easiest chapters. And another trick here. What is the name of this? Is this alpha cell bios or beta cell bios? Why?
Because the anomeric carbon dioxide.
يعني ما شاء الله يعني. Okay, lactose, the milk sugar basically. Here's the difference. Maltose and cell bios, they used glucose. Lactose wants to be different. What will it use? It will use galactose and it binds to glucose. But you have to know that it's important to know that which one binds to who. So is it glucose binding to galactose or galactose binding to glucose? Yes. Why is it important? Because the sugar who's going to initiate the binding is going to use its anomeric carbon. So it's saying, I want to create a bond with you, I'm going to sacrifice this carbon, or this hydroxyl group, basically. So this galactose used its anomeric OH to connect to carbon number 4 on glucose. So here, how do you, basically, by the way, I actually learned this just like a few weeks before preparing this. Look at this structure. Is this a glucose or galactose? Why?
The OH is up.
Carbon 4, exactly. And this is a glucose. So who sacrificed their anomeric carbon? Galactose. So who gets the right to name this sugar? The bond, not the sugar. Galactose. So this bond is facing upwards. What's the bond? Beta or alpha? Beta. And 1 to 4 or 1 to 5? What? 1 4. So we decided that the bond is beta 1,4 galactose glucose. Who names the sugar itself?
The anomeric carbon of the glucose.
Mashallah. So we have the anomeric carbon here. Since it's down, it's alpha what? Guys, you need to start memorizing the names of the sugar. Alpha lactose. And if it's down, I mean if it's up. Simple enough. This sugar, mostly you find it in milk. And by the way, maltose and cell biose don't naturally exist in nature. Why? Because maltose is an intermediate product of starch hydrolysis, meaning that when you eat starch, or you eat potatoes basically, the first digestion begins in your mouth, and this is mentioned in your book actually. It begins digesting and it forms maltose. Then when it moves into your stomach, intestine, whatever, this maltose gets broken down even more, and then it gets converted into glucose. So maltose naturally does not exist in nature, and this is important. They love to focus on small details. Oh, this one exists in nature, this doesn't. So is the case for cell biose. Cell biose doesn't naturally occur in nature. However, it is a reducing sugar. And you see these, I purposely put that it was not mentioned. You don't mention in your book, I think from what I read when I was reading the book, it's not mentioned that they're reducing. However, there was a question on this. Which of the following is not a reducing sugar? It was something like that. So, you need to know lactose, cell biose, lactose, reducing sugars. Which exist in nature? Which exists? Lactose only. Cell biose and maltose don't exist in nature. So, oh, wait, move to sucrose. Okay, wait. What's the difference between these two lactose molecules? Which is basically the alpha beta lactose. Amazing. Okay. Here, this sugar is the sugar which likes to break the rules. Personally, I don't know about you, but when I was foundation, I was studying, I was like, why is it alpha beta 1 2? I don't understand what's going on. So, sucrose is a disaccharide where glucose binds to fructose and fructose binds to glucose. It's a confusing, so the order, in this case, I couldn't really pay attention to the order because it was just going everywhere, the bond. But this bond is classified as alpha 1 2 beta. Why? I want you guys to notice something here. That fructose used its anomeric carbon and glucose used its anomeric carbon. So who gets the ownership to decide the name of the bond? Is it glucose, fructose, or both? Both, exactly. So this glucose has its OH pointed down. So what's the naming? Alpha or beta? Alpha. And this fructose has its OH pointing up. Alpha or beta? Beta. So we can't ignore one and include one. So they said, let's take both. Alpha 1 2 beta. Is this clear?
Is this always like this?
Yeah, sucrose loves to be like this. Just معطول. Is this clear? Because this was a really confusing point for me, so I don't know what to. Is it clear?
What is it 1 2? And first second carbon?
The first carbon of glucose connects to the second carbon of fructose. If you're confused on how is this the second,
Yeah.
this is the first.
Does fructose always come in this form?
Usually fructose loves to be in this form. So most likely when you get an exam paper and you check, most likely fructose is going to be in this form. How can you check that this is really fructose? Just look if there's a CH2OH here, CH2OH here. Simple enough.
And sucrose is always alpha 1 2 beta.
Sucrose always alpha beta 1 2. Guys, by the way, for the bonding, if they bring you a sugar, ask you what bond is maltose, always it's going to be alpha 1,4 glucose, always. So the naming of the bonds themselves, for the examples they listed, this is a fixed naming. However, they can give you an unknown sugar with a bond and ask you what bond is this, or what's the name of this bond, what's the name of this sugar. Okay? And an important point that sucrose is a non-reducing sugar. This is in one of the exercises of your books where it was asking which of the following is a reducing sugar, and sucrose was there. I don't know if you guys solved them, but they're really useful. So, moving on to polysaccharides. What's the classification for a polysaccharide?
15 monosaccharide.
Huh?
That's one monosaccharide.
No, I mean, what's the classification? So from this to this unit, we consider a polysaccharide. What is it? Come on. It was in the first slide of the lecture. I mean, not lecture, but the session. 10 to 15. Well, guys, why are you shy? Answer with confidence. Polysaccharide is more than 15, or 10 to 15, but in this case I put more than 15. Yeah, أريحكم. It's divided into two categories. We have heteroglycans, homoglycans. Heteroglycans, basically, we have glucose, mannose together and they form a polysaccharide. I don't know if this is an example in your book, but I just want to make you understand the idea, is that heteroglycans, different monosaccharides are used. While homoglycans, we have glucose, and it forms different structures, but it's still glucose. Homoglycans, such as starch, glycogen, chitin, and cellulose. By the way, guys, is chitin cancelled for you? It was cancelled for us last year, which is why I didn't explain it that much. But no one knows? Amazing. So, and cellulose. Starch, glycogen, and cellulose, when you hydrolyze them, and guys, what's hydrolysis reaction? You learned this in the first chapter. How? Yes. So, you hydrolyze this sugar by adding water, they give you D-glucose. All of them. Starch, glycogen, cellulose. But we of course have exceptions. ما في شيء بس. Chitin, when hydrolyzed, yields N-acetylglucosamine. Where did we say this? And what's the sugar here that we attach to? Glucose. This is in the monosaccharide derivatives, but it's good that you know that. Okay, so starch. By the way, guys, don't get confused between sucrose and starch, because I got confused while making the PowerPoint myself. So, starch is the principal energy storage molecule in plants. So, if you guys take a human, you check his cells, are you going to find high quantities of starch? No, of course not. And then, starch, we said it's a homoglycan, meaning that it has one type of sugar, but this sugar can form different structures. So for example, starch has two polysaccharides, amylose and amylopectin. Amylose is a linear polysaccharide. It makes your life easy. I'm just a linear polysaccharide like this. I only have alpha 1,4. Think about it, guys. Will there be any branching if the bond is just like this? So it's a linear polysaccharide. Linear polysaccharide. And since it's linear, it can flip on itself. It can do like this. I don't know how you want to imagine it, but it's a linear structure. It can form a helical shape because it's a linear structure. Okay? Amylopectin, same thing as amylose, except that it has an extra bond, alpha 1,6. So, they give you a question. What's the difference between amylose and amylopectin?
The branch is linear. Amylose is unbranched, however the amylopectin is branched.
Why is it branched? This alpha 1,6 bond here is this. And you see, normally if you just remove this, you have amylose. normal amylose, just linear alpha 1,4. But add an extra bond, which is alpha 1,6, and it creates this yani, branch structure. Then you have amylopectin. Is this clear? Okay. An important point to note is that they love to confuse you with this, is that amylopectin has the branches, but it happens every 20 to 25 residues, meaning that it's not a highly branched structure. There's branches here, here, but there's space between them. This branching prevents the sugar from forming a helix shape. So, can amylose form a helix shape? Yes. Amylopectin can it? Why? Branches. First part of digestion, and I mentioned this, happens in the saliva of the mouth by an enzyme called alpha amylase. What's the bond here? Why?
The anomeric carbon had the OH of this anomeric carbon was down. So
Exactly.
now the bond is also
Exactly. Alpha 1,4. How can we break this? Just introduce an enzyme, alpha amylase. Because this is an alpha bond, so we're gonna bring an enzyme which specifically breaks down alpha bond. This is the first part. It continues into the intestine, and then I don't think you need to know all this because this is just biology basically. But an intermediate product is maltose. And this is why we said maltose doesn't exist in nature. Because normally you wouldn't find maltose unless you break amylose or amylopectin, same thing. Then, didn't we say that when starch is broken down, it gives you glucose? Hello? Why does it give you glucose? When here clearly it gives you maltose. We said maltose is an intermediate product of starch hydrolysis. Meaning when you're baking starch, you're gonna get maltose on the way, which is gonna get converted into what? Glucose. Why did we say glucose? Starch, glycogen, and cellulose, when hydrolyzed, all yield D-glucose. Are you connecting the dots? I feel there's confusion in this part. Okay. So, glycogen. You guys learned about this in your muscle quiz. Where is it found in highest quantity?
in the liver and stored in the muscle.
Did you just from here? Oh, okay. Okay, good. So, this glycogen follows exactly like amylopectin. Has alpha 1,4, alpha 1,6. Only difference is that it occurs every 8 to 12 residues. See how this simple change in the repetition of the bond created a whole new polysaccharide here. This polysaccharide is found the highest quantity in vertebrates, so humans, mammals, things like that. So, found highest abundance in liver and muscle cells. Why muscle cells?
Because they use it for energy.
Energy, directly. We need energy. We have glycogen, break it down, glucose. It contains many non-reducing ends. Where are the reducing ends? It's as if this is the figure in Thailand here, but these are the non-reducing ends. Break them down quickly so we can digest this and we can get energy. And I saw from someone that cellulose was written slide, that you guys studied this from the PowerPoint.
Yes.
Okay. So I didn't explain it because it was written slide. So this is for my last part and now it's Faisal.
So before I start, I want to delete all this. I mean, Okay, so I go over the heteroglycans. So we have three types of heteroglycans. We have N heteroglycans, O heteroglycans, and the glycoamino. Okay, so a very important point about them. So N heteroglycans have beta glycosidic bonds. O heteroglycans have A alpha glycosidic bonds, and the glycoaminoglycans are negatively charged polysaccharides. That's just like a basic introduction, and I'll go deeper into them right now. Is the mic working? Okay. Yeah. So I'll just give you a general review of heteroglycans. So heteroglycans are large carbohydrate polymers made of different monosaccharides. That's an important part, okay? So they have two types, N and O glycans, which are attached to proteins, and the glycoaminoglycans in the extracellular matrix into a JPI anchor. And like I just put this photo because this like kind of represents the structure of them when I show you on the next slide. Next two slides, and yeah, the one after this. So we'll go over the heteroglycans. As I said, they are linked by beta glycosidic bonds, and they have and this bond is between the anomeric carbon of the core and acetylglucosamine and the side chain of nitrogen of the asparagine residue. And you know asparagine from your protein chapter. And we have commonly observed sugars, and I think you have to know this, right? You have to know the structures, like memorize them as much as you can. Mannose, galactose, and acetyl numeric acid, and glucose. Okay, so we have three major types. We have the high mannose, complex, and the hybrid. So can anyone tell me like the general thing, what they notice? Like what they notice is the same? I want here, I want all three. Okay, can someone raise his hand and speak loudly? Anyone up here? Okay. And the asparagine. You forgot the asparagine. Yeah. Okay, so that's right, yeah? Okay, so if you see, this one is the high mannose, this one is the complex, and this is the hybrid. They all have this, you see this, okay? This one, it's all the same, and everyone, it's the same. And high mannose, we just have mannose. Everyone, just mannose. That's like a way to memorize it. High mannose, just mannose. Complex, we have everything. Everything is here in the high. So we have the base, which is there for everyone. Then we have more N-acetylglucosamine. And then we have galactose, which we don't have in the high mannose. Then we have salicylic acid, and another salicylic acid, and then another N-acetylglucosamine, then galactose, then salicylic acid. You know, I don't think you have to know the structure, but like I'm just letting you know that the complex one has everything in high amounts. The hybrid one has everything, but in lower amounts. That's the general idea of it. Okay, it's fine. Okay. So now we'll go for the heteroglycans, and if you see this color, it's different color. Why? Because it's a different molecule. And you might see the N-acetylgalactosamine, and you might think like it's the same thing, but it's not the same thing. It's a different one. So the core is linked to a different molecule, and it's linked via alpha glycosidic bond to the hydroxyl oxygen of serine or threonine. See, serine or threonine. Then we'll go to the structure now. So we have a serine or threonine. Then we have an hydroxyl oxygen that it binds to this one, this long name. I don't want to know. By an alpha hydroxyl bond. Then we have this, and then N-acetylglycosamine, and then salicylic acid. That's the basic structure. Then we have collagen. Okay, collagen. It has galactose, or galactose glucose. You have to know this. This is an important part, and it's linked to the side chain of hydroxyl oxygen of 5-hydroxysilane, lysine, I mean. So now we'll go over glycosamine glycans. We have 5 different groups. So like you can read them now, but like does anyone know the difference? Like there's one of them has a main difference. If you don't know, we will discuss it over the next slide. Okay, we'll discuss it. يلا. Okay, let me read them first. ارجع. So we have hyaluronic acid, converted sulfate, dimethyl sulfate, and heparin and heparin sulfate, they're grouped as one. I don't know why, but like they're grouped as one. And keratan sulfate. So the gags, they are linear polysaccharides. And you see like everything that I made bold and green are like important things that might come in the exam. Like they're really important. Like you have to know that gags are linear and they have repeating disaccharides and they contain sugars of amino derivatives. These are for you that you have to know. And like N-acetyl hexoamine sulfate is also present, but this is the exception I was talking about. Except in hyaluronic acid, we don't have this molecule. We don't have it in this one. So this molecule we replaced by N-acetyl glucosamine. Do you get this point? Okay. So these disaccharides contain carboxyl and sulfate groups, and that's why they are negatively charged because of the sulfate groups. So they have many negative charges at physiological pH. Does anyone know the physiological pH? Yeah, صح. So these charges repulse, does repulsion action on gags and separate them from each other, and they are inflexible and strongly hydrophilic. Yeah. Glycoconjugates. So they are covalently linked carbohydrates to proteins or lipids. So these are called glycoconjugates, and we have two classes of protein: proteoglycans and glycoproteins. Can anyone give me a general difference between them? Like the main difference. Like which one has more carbohydrates than the other? That's what I want.
The first one has more carbohydrates.
صح. تعرف percentage or لا? You don't have to know the percentage, just okay. So we have glycolipids, which are sugar-containing lipid molecules, and they're found in the outer surface of the plasma membrane. You have to know the locations. Locations are very important. They can ask you about this. Okay, so it's a viscous network of macromolecules secreted by cells such as fibroblasts. Many of these molecules are glycoconjugates such as proteoglycans and the glycoproteins, like laminin and fibroconnectin. This is just an explanation of the extracellular matrix, so like I'm just reading it because it's an easy part, and I don't think the question will come from it. And like together with fibrous proteins such as collagen and elastin, these components give the ACM, the extracellular membrane, its major role in cellular development, differentiation, mobility, and wound healing. This is the important part. Okay, this is the important part. This is what I want to focus on. Like, why does this happen? Because they have a lot of viscous, they have a lot of things. That's why it's viscous. So these things join together to enter the cell and affect these things. So that's why it has cellular development, differentiation, mobility, and wound healing. Yalla. Proteoglycans, the one we said that has an extremely high carbohydrate level. Why? So it reaches like 95%. It's like usually 95%, yeah, carbohydrate. So these molecules are on the cell surface or are secreted into the extracellular matrix. You have to know these locations, and very important. And these proteoglycans contain gag chains linked to the protein molecules. This is also an important part, which is linked by N or O glycosidic bonds. And proteoglycans are produced in the Golgi apparatus. You have to know this, which is the same place as the gag. And they covalent link to a protein which is formed in the rough endoplasmic reticulum. This is also an important part. I just put this photo because like it really looks like a proteoglycan. If you saw the structure of it in the book, you don't have to memorize it, but like you have to like recognize it. So like you can see here, this is the core protein, and then these looks like the carbohydrates going out of the protein. Like anyone saw the structure of the proteoglycan before? Okay. So they have negatively charged because of the gag chains, as we mentioned before. So this traps a lot of water. So like it covers much more space than other molecules. So this gag causes it to have extreme strength, flexibility, and resilience. Okay, I want to ask you before I explain this. Is this part included with you? Does anyone know? If you don't know, I'll just explain it and you can check later. Okay, I'll just explain it. Okay, proteoglycans have intercellular walls. For example, this molecule, I don't like it's in mast cells. Do you know what mast cells are? Or did you not take it yet?
We did.
Okay, can you tell me what mast cells do?
they secrete anticoagulants and
Okay, yeah, that's the general idea. Okay, so they're in masters, and they're linked to highly sulfated heparin gangs. Why is this? Why does this happen? Why does they do it? To protect positively charged molecules, such as histamine, like he said, which is produced by the mast cell, and proteolytic enzymes. Okay, so we have glycoproteins. So, what do you know about glycoproteins? Can anyone tell me anything?
Sugar is attached to protein.
Yeah. Okay, so they're covalently linked through an N or O linkage, and the carbohydrate composition of varies. Like it can be really low, up down to 1%, or like 85%. But generally, proteoglycans are more. And like, how do you recognize it? Proteoglycans end in glycan, sugar. So that's like you would know it's mostly sugar. Glycoproteins end with protein, so it's mostly protein. That's a way to memorize it if you want. So the carbohydrates found include monosaccharides, disaccharides, and they're attached to the structure collagen and the branch oligosaccharides. And why that with this? Because it represents like the idea of glycoproteins. Like imagine the bottom of the cupcake is the protein. It can have little carbohydrates or many carbohydrates. So like I just put it like to link things. Yeah. So this is the structure I was talking about. You have to know that glycoproteins are transmembrane, while glycolipids are only in the extracellular membrane. And here you have the structure. You can see the co-protein going, and the carbohydrates are here, and you can see the glycoproteins here. Did you get the idea? Okay, so there's an absence of glycoproteins in ionic acid, sulfate groups, and disaccharides repeating unit. And they are linked to the polypeptide by either N-glycosidic or L-glycosidic, and N-glycosidic are linked to the asparagine, as we said before. And N-linked oligosaccharide structures are formed in the endoplasmic reticulum and Golgi complex. Okay, so glycoproteins. They exist both in the soluble and membrane-bound forms. You have to know this. It's an important thing. Like we have blood clotting factors, complement components, and several hormones, such as FSH. Does anyone know what FSH is? It's more biorelated.
Sorry, molecular stimulated hormone.
What does it do?
Stimulates the
Awesome.
Doesn't it allow the follicle to stay functional?
Yeah, you can say that. But you don't have to know this. This is bio, not biochem. So carbohydrate groups in glycoproteins assist in protein folding, stability, and recognition, and protect proteins and for proteolysis by shielding the polypeptide chain. I don't think it's important, that's why I just went over it really quickly. But like, read them, read everything. Okay, now into questions. Okay, this question, I want to answer them quickly because we don't have very much time left. Anyone? If you don't answer, we'll go straight to the mentee.
يلا guys يلا.
Yeah, B. The second one. So we'll go straight to the mentee. No, not A. Yeah, B. Okay, this is the last one. Last one.
This is an important one. This is an important one.
B.
Yeah. حصل نفسك عادي يلا. Okay, we'll go to the mentee now. شكرا حصل mentee.